Okay. So the next thing we're going to start talking about is structures and stereochemistry of alkanes. You're going to notice what we kind of do is we have a sort of set format for this course, okay? So at the beginning, I just have to review so much material and introduce you to concepts first, right? And then what we're going to basically do is we're going to talk about different functional groups. So each chapter will essentially be a functional group, and then we're going to cover various different topics in it. For example, like structures that happen with it. We're going to talk about, in this we're going to introduce stereochemistry, and then every other one will have stereochemistry, okay? And then eventually, once we get what they look like and you get comfortable with the functional groups, we'll start layering in reactions, okay? And then when we get the spectroscopy, next semester you'll start getting spectroscopy with that too. Okay. And more advanced reactions. Okay, so these are the hydrocarbons. Again, hydrocarbons are molecules that are made of carbon and hydrogen only. Technically, if you have any substituent on it, that is no longer just a hydrocarbon, is it? But you can call it a substituted hydrocarbon. See how the game we played there? This is the alkanes. Again, there's no double or triple bonds in an alkane. It's just a hydrocarbon. This is the alkenes. It's going to have at least one double bond in it. We have the alkynes. That's going to have at least one triple bond in it. And then we have the aromatics. This is going to have a benzene ring. Okay? Right now, we'll only talk about benzene rings. There are other things that could be aromatic, but benzene ring is by far and away the most common one. And right now, you just don't need to worry about the other ones. Okay, so in the case of an alkane, all the carbon bonds have to be filled with hydrogens, don't they? Okay, you can call this fully hydrated, all right? Meaning hydrogens are everywhere they can be. The general formula for an alkane is going to be the number of carbons, so Cn, N being that number of carbons, right? Is going to have hydrogens that equal 2 times N plus 2. An easy way to think of this is every carbon you have has 4 positions, right? And we can do that sort of a north, south, east, west, right? The 4 cardinals. Okay? So think about that. Have that in your head right now. So when you do this, if it's in the middle of the compound and you have 2 carbons on either side, how many hydrogens would you have to fill that in? 2, right? Okay. And that would be called a methylene, by the way. And so most carbon chains, almost all the carbons are just going to be repeats of that, aren't they? So they're going to have a carbon chain. You have the chain, of course, 2 carbons attached to each end to make a chain, and then 2 hydrogens. And that's where the 2N comes from, okay? If it's not cyclic, then you also have to have endings, don't you? And so the carbons at the end of the chain, they don't have any other carbon attached at the end, or do they? So what do you have to put at the ends of your chains? Hydrogens. Okay? And that's why the plus 2. Does that make sense? Okay. This formula isn't really needed as long as you understand what the hell an alkane is, right? Yeah. These are going to be found in everything from natural gas to petroleum. This is typically what you would call natural gas. Would be like methane, ethane, and propane in a mixture. The natural gas in your home is mostly methane, okay? Though you can buy propane tanks to do the cooking with. If you have natural gas in your home, that's kind of getting phased out. Gasoline is going to be things that are around the size of octane, okay? By the way, the straight chain form of octane is not what octanes at the pump actually means. The octanes at the pump is a very specific organization of those octanes, which would give you 100. on that scale. Okay? And then they burn other stuff, and that gets a rating based on how it burns. And then they mix the stuff so it's within a certain range of being able to burn properly. Right? Okay. Just to head that off so you don't get confused and go, octane. Yeah, it's a little bit more complicated, but yes, it does refer to the octane as in the structure with 8 carbons, okay? Just not straight chain. The smaller alkanes are going to have very low boiling points, therefore they are gases, and this is why they show up in things like a gas for a burner, right? The longer chains will again have more London dispersion forces, and so they will be liquids, solids at room temperature if you get large enough. Okay? Anybody know what they do with the solids at room temperature alkanes? So you know they have natural gas, right? We burn that. Okay, we have things like gasoline at the pump, right? That's sort of the next band. Okay, that's the stuff that's liquid mostly at room temperature. But if you leave it sitting on a hot day, it's going to evaporate, right? Then we have diesel, and that's a little bit heavier, isn't it? Okay, you notice that doesn't evaporate as easily. All right, does anybody know what the next step is? Things like engine oil. Okay, the non-synthetic ones are just the next step of petroleum. So longer chains. Anybody know what they do with the stuff that doesn't evaporate at all? They don't bury it. Anybody ever seen the road out there? Asphalt. Yeah. So that's the stuff that doesn't evaporate when they burn and heat the stuff up. They do a fractional distillation. And they take the different fractions off at different heights. Okay? That's that thing that looks like a candle, has a burning end, and it has a bunch of pipes coming off. All right? You guys ever seen a refinery? By the way, that's actually the real reason like gas prices keep going up, is because they've blocked the production of refineries in the U.S. So we're maxed out at refineries. We only had 4 of them at one point. Yeah. So yeah, that's actually the biggest problem. They blocked 2 productions of refineries in like the last 5 years. Anyways, so the alkanes, as you get heavier, they are actually solids. Even when you heat them up, they only go to liquid. And that's actually how you make asphalt. You take that, heat it up, it's liquid. You mix it with a bunch of rock, small rocks, and then you spread it out. And when it spreads out, it'll cool down, and it'll become solid. Anybody been to somewhere really hot that's like 130 Fahrenheit? No? If you go down to like Las Vegas in the summer, it gets like that pretty consistently. And I used to, have a motorcycle, and I worked down like laying pipe and stuff around Las Vegas area. And I used to, if you put your kickstand out and lean the bike over, you'd come back and the bike would be laying outside and the kickstand would punch a hole in the asphalt. Made that mistake once. That was pretty damn funny. Because it's a bit like peanut butter when it gets that hot. Okay, so this is some different examples of the alkanes. Hopefully everybody kind of had this already figured out. Remember, you can have the straight chain one and branched ones. Does anybody have any questions about the naming of alkanes? Who here thinks you could survive this course without knowing how to name these chains of carbons? Good. I'm glad nobody raised their hand, because you definitely couldn't, right? Basically, this is the language you have to be able to talk. Okay? Okay. Again, these repeated units of CH2 are called the methylene groups. The groups that are CH3 are called the methyl groups. Okay? So this right here is a methyl. That's a methylene. That's methane. Everybody okay? Methyl is the CH3. Yeah. So like, for example, these are each methyls. This has 3 methyls. Okay. These 2 groups in the middle here are the methylenes. Bless you. So the methylene groups is known as a homologous series. And that's because what you get here is a series of compounds that differ only in the number of methylene groups. This is also how you typically write out very long hydrocarbons. Is you would actually put CH3, CH2, and then put parentheses around it, and then the number of those. Okay? Because at some point you get hundreds of them, like candle wax and stuff, and it just doesn't make any damn sense to do anything like that. All right. So again, these are some of the different small alkanes. I think you're all good so far. These are the physical properties. Again, remember, as we get larger and straight chained, those are going to have higher evaporating points, higher melting points, right? Okay. Because as you get larger and straight chained, you have more London dispersion forces that happen. Is that making sense? Okay. All right, very good. By the way, that's how you draw them out of. That's how you can tell the homologous series that we're talking about. Right there. See how we just changed the number in the middle? And see, it even more distinctly shows you the hydrogens as caps here. Yeah. Okay. So this right here is constitutional isomers. So notice that if we do the condensed formula for butane, butane is C4H10, right? And that's that CN 2N plus 2 for the hydrogens, isn't it? Can everybody see that? 2 times 4 is 8, plus 2 is 10. Okay. And so, does that adequately describe it that we can now say, I know exactly what I have? No, actually. Okay? There's actually 2 different compounds that both have that condensed formula. Right? They both are alkanes. They both give you C4H10. Okay? That's N-butane. That's the straight chain form. And we have the branched form, which is the isobutane. Right? And these are what are referred to as constitutional isomers. They're compounds with the same molecular formula, but the carbons are connected differently. The only way they're different is the connectivity, how they're put together. Okay? Okay. They have no different functional groups, nothing else. Now, interestingly enough, this actually means they have different physical properties, don't they? This would have a higher boiling and melting point than this one. Okay? So you could actually separate these. Wow. Through like a distillation, right? Okay. This is the pentanes. Notice as you get more carbons, you're going to get more constitutional isomers, aren't you? Okay? Because you have more ways of arranging them. So this is the N-pentane. That means the normal straight chain one. This is the isopentane, which is that iso group right there. See how that's the iso? Okay. And then this is the neopentane. Neo being that it's branched in all the directions. See that? Okay. All right. So to clarify these, so we don't get things that are all these different constitutional isomers all mixed up, so we don't know which one's which, and then we do 20 publications all in the same compound and never reference each other. They came up with a naming system, and this is the International Union of Pure and Applied Chemistry. By the way, before the units and naming systems were put in place, they used to have a problem in Paris where they'd have a college literally that you could throw a rock from one science building to another and hit the other one. And they would publish stuff on the same compounds, same properties, and they would never realize they did it because they named them different things. Yeah. Silly, right? But it's how things worked for almost all of human history. Yeah. Then standards got applied, and now we follow the standards. And now that happens rarely. Still happens though. Physics actually did it recently, back in the like 2005, 2008. They came up with a new spectroscopy that they called terahertz spectroscopy that happened to be 100 years old and was called far infrared in chemistry. And I'm sure that's happened some other places, but yep, there's no standards for that one. Whoops. Anyways, so this is again the standard method. It's used internationally to name compounds. When it comes right down to it, everybody has a name that is then associated with that compound for an IUPAC name. This uses the longest chain of carbons as your main chain. So you always identify the parent or main chain first, okay? And which one is that? It's going to be the, come on. Which one is it? What's your main chain? The longest chain. You got it. Okay, so some of the common names that are kept are going to be methane, ethane, propane, and butane. There are common names that have been sort of grandfathered into a degree, but mostly it's constrained within the IUPAC naming method. Basically, they started it from there. Okay? Keep in mind, does a chain work if I have two objects that are completely separate? Is that a chain anymore? Okay, so keep in mind that naming actually means something, right? So I'll show you in just a bit, but I get a lot of problems with that. Students, it's one of the most common mistakes. Okay, so here's the rules for the IUPAC naming. You kind of want to have these rules down well enough that you just follow them automatically, which will happen with practice, of course. Rule 1, find the longest continuous chain of carbon atoms and use the name of this chain as the base name of the compound. This, funny enough, this rule right here is actually where people screw up the most often. Okay? Again, longest continuous chain, right? If you have to skip over something and move from one place to another, or they're not attached, that's not a continuous chain, is it? Okay? Rule 2, number the longest chain beginning with the end of the chain nearest a substituent. Basically, it doesn't matter left or right, okay? Because you writing it left to right has no bearing on that molecule at all, does it? That molecule's not staying left to right in space because some reason, right? It's rotating and flipping and bouncing around, isn't it? All right? So you made a just completely arbitrary decision when you write something left to right, okay? Because English, yeah. Or I should say European languages in general. You could have written it top to bottom, couldn't you? That would have been Japanese, okay? Or cuneiform. Name the number 3, name the groups attached to the longest chain as alkyl groups. Give the location of each alkyl group by the number of the main chain carbon atom to which it is attached. And then you're going to write the alkyl groups in alphabetical order, regardless of the position in the chain, just so you can find them easier. So where they are on the chain is given by the number of the carbon they're attached to. Okay? And that's the same for any substituent. What is a substituent again? Anything that substitutes for the place of a hydrogen, right? That's not a hydrogen. Okay? All right, let's do some examples. This really is not hard to do. You just need to practice. It's like any language. If you practice it, you'll understand it. If you don't practice it, you will never understand it, right? Okay. And so, practice, practice, practice. Make sure you practice this right away, by the way, because if you wait, you will not remember anything. You have to completely restudy to do it, okay? And it'll be wasted time. All right, so find the longest chain of the consecutive carbons again. So here we have an example. So the first thing we do is we go ahead and look for the longest chain. This has to be continuous. So we go ahead and count. 1, 2, 3, 4, 5, 6. Notice I did not count the same as them. Okay? Why did I not count the same? Because I want to make a point, don't I? Doesn't matter if you start left or right. Okay? Now let me point something out as well. What if you went like this? 1, 2, 3, 4, 5. Is that the longest continuous chain anymore? It isn't, is it? And that's one of the reasons why they've drawn it like this in your book, okay? Is every book is going to draw it like that to try to break you from the idea it has to be left to right. Now, when you write these things, you're probably going to write them left to right. Just because it's easier, right? So yes, you can draw it, with this flat on there and this one pointing up. That would have been fine. There's no reason they didn't do that, okay? They just did that, so they're trying to break you from reading it left to right every time. Get you out of that mindset. Okay. By the way, these chains are always twisting around anyways. Remember that it's a chain. It's just like a chain. Like if you were holding a chain, it doesn't just magically straighten out for you, does it? It twists everywhere. Okay. So again, what about this? 1, 2, 3, 4, 5, 6, 7. What did I do wrong? Yeah, not continuous, right? Yeah, this is one of the leading causes of mistakes. By the way, when you're writing these from names, I know I'm getting a bit ahead of myself, but please double check and count, okay? When you write these, people have a big tendency to just repeatedly put carbons and put 1 or 2 extra, okay? So always count out your number of carbons. Hexane, 6. Do I have 6? Okay? Okay, does anybody have any questions there? Everybody got why I counted it like that? Okay. Okay, so once you've counted your longest continuous chain, what do you have to do? You have to number it, yeah. How do you determine which side gets the lower number? Kind of. Yeah, something interesting is there. Or the substituent, right? You're numbering the substituent the lowest number possible. Okay? So if I count it 1, 2, 3, 4, 5, 6, 3 is my lowest, right? If I counted it this way, 1, 2, 3, 4, see how that would be a higher number. If it doesn't matter, then yeah, you totally get to decide. Right? It doesn't matter at all then. In fact, then it would be symmetric.
So if it doesn't have a group attached to it, it doesn't matter?
Nope, doesn't matter at all.
But if it does have a group attached to it, then you need to do the shortest.
Yes, yep. If it has any substituent attached, then you always need that number to be the smallest number possible. Okay? And if you end up being the same on both sides and it has another one attached, you go for the shortest one on that. Okay? And you continuously try to get the smallest numbers possible for your substituents until it stops being, optional. All right. Okay, so remember that this one, this longest continuous chain, this is my main chain, right? And so everything gets named off of that. Or another way of saying that, remember the ethane, propane, hexane, etc.? those are my main chains, okay? The ethyl, methyls, those sort of things, ending with YL, those are substituents, all right? You can also call the main chain parent chain. I've seen that terminology quite often. It is very common, okay? You'll catch me using it every now and then. So right here, we have two options for a main chain. If you have two options that are the same number of carbons, then what you want to do is simplify your life, okay? And simplify your life means you go with the one with the most substituents, okay? You don't know this yet, but naming this group would actually require more work, right? If you have complex substituents, they require more work, and the name becomes longer and more complex. So again, you go with the one with the most substituents, which in this case is this one, right? 1, 2, 3, 4. 1, 2, 3 substituents. So 4. Okay. Number 2, now we're numbering the main chain. Again, you always minimize that number for your substituents, right? And so right here, we see that we have an option where we can go 1, 2, 3. Alternatively, we can go 1, 2, and that gives us a 2 for our first substituent, right? And so which one's the correct one? The one that minimizes that number, 2. This one would be incorrect, wouldn't it? Okay. It doesn't really matter what the substituent is for this numbering, okay? Like if you have a longer substituent, that doesn't matter, all right? I know longer seems like it'd be more important, but it's not. Trying to head off that. Okay. Anybody have any questions there? Once you've numbered that parent, everything then gets the number of the carbon it would be attached to. Okay? So for example, here, this has 7 carbons, so that name for the parent would be what? Heptane, right? Okay, you see the heptane? Okay, now we have to do the substituents. Our numbering is going 1, 2, 3, 4, and so we have 1, 2, 3 methyls. 3 of those means tri, right? So we're going to name that trimethyl, okay? We'll put where it is substituted on in front of it. 2, 4, 5 dash trimethyl, okay? We separate each of those numbers out with commas so we can delineate which one's which, right? If we happen to have more than one on a single carbon here, if we had like another methyl here, we would just put that number twice, 4, 4. That makes sense? Okay. Okay. And so we would then do in front of that ethyl, because we have an ethyl here. We only have one, so we don't have to do anything else, just ethyl. And we put the number that's on. That's on the 3rd carbon. See that? All right, when you first do these names, or if it's particularly complex, make a cloud of your terms, okay? Don't put them in order until you're ready. So parent, heptane. And then I'd put, not necessarily right in front of it, I have methyls, trimethyl, 3 of them, okay? I put that numbering.
Is it put the 3 ethyl first for the 2, 4, 5 trimethyl?
It does. It's alphabetic, not including the numbering prefix. So you ignore the tri here. That doesn't matter for the alphabetic order. Okay? The ethyl is in front of the methyl because it's eth-meth, right? E versus N. Okay? Yeah. Be careful you don't try to put that tri in there, because then you'll have things running around everywhere. Okay. Whenever you do these, I highly recommend that you don't assemble them until you have all the pieces together, okay? So like write the 3-ethyl, the 2,4,5-trimethyl, and then the heptane as separate pieces. And then organize them based on alphabetical order for the prefixes in front of the heptane. Does that make sense? If you try to write this as one go, you're going to do things like, oh crap, I forgot the methyl. Okay? Or I forgot a number, and then you're going to have to erase the whole thing, re-expand it out, get it in there, right? And it'll become a mess. Okay. So this is rule number 3. This is naming your alkyl groups. These are the naming patterns for those different the most common alkyl groups. This would be the alkane with that number of carbons. This is the alkyl substituent. Notice even the alkyl actually tells you how you name them, doesn't it? Alkane, alkyl, right? So what you're going to do is take that alkane name that you would have done for the main parent, and you're going to change the A and E to an IL, YL. Okay? So methane becomes methyl. Ethane becomes, come on, ethyl. Very good. How about pentane? Pentyl. You got. Now there are common namings for these. For example, this is a common name for pentyl. Okay? And that's going to be in amyl group, but the common names are a bit less important, right? There's something that you should learn to some degree, but I'm not going to spend all my time testing you on them. There's something that gets used a lot in industry because of legacy. Okay? And they don't want to change the labels. That's it. All right. So this, for example, is 1 carbon. This is a methyl group. Again, that's ethyl group. That's the propyl group. If you want to stress that that's a straight chain, it would be N-propyl. Though technically, as long as you just say propyl group and nothing else, that's straight chain. Right? Isopropyl then, remember that makes that V shape. It's the 3 carbons in an L shape. That's the butyl group, isobutyl. This is if you don't have that substituent off of that substitute chain. See how you have that CH3 off here? If it's not at the end here and making that V shape, which would be iso, right? That's actually sec, for second off, right? Okay. And so this is sec butyl with this substituent right here. This is tert butyl, and tert means literally tertiary, right? Okay, like a tetrahedral shape. Okay. So tertiary, fully substituted. Okay, you can also call it T-butyl to shrink down so you don't have to write as much. Let's apply some of these naming rules. So again, right here we have how many carbons? 6. So that's going to be what? Hexane, yeah. What are our substituents? We have a CH3, which is called methyl. And then we have a 2-carbon one, which is called ethyl. Very good. Is there any particular reason I numbered down here, I counted these ones versus these ones? Oh, this would be continuous, right? See? 1, 2, 3, 4, 5. That's still connected to that carbon. 6. And this was 6. I mean, it would be branched down here then. Yeah, you choose. Yeah, it's arbitrary. There's no difference. Remember, this is a chain. So like if you had a chain, you could arrange it so one part of the chain comes up, one part comes down, right? And you could move that around any way you wanted, right? And so, yeah, we just arbitrarily arranged it that way. There's no reason at all. I could have just easily went up here. This would have been the ethyl. It would have been substituted the same place, right? So, no reason at all. So I'm on the second position here. Why did I choose this side? Why did I number it 1, 2, 3, 4, 5, 6? Is it because it's on the left? You got it. Yeah, this will give me 1, 2, 3, wouldn't it? Yeah, it's a higher number. Okay, and so once I've got this, I have a hexane. It has a 2-methyl, 4-ethyl. How do I start putting this together? What comes first? The ethyl comes first. Why does it come first? Alphabetical. E becomes before M. Okay? And then I'd put the 2-methyl. You place dashes in between the numbers and the names. If my names come together, I can just go ahead and put them together as one word. Okay? It's not technically wrong to put a dash, especially if you're going to be going on to like a new page or something. Or if that might happen, some people do that. Like in publications and stuff, because they don't know whether it's going to go. Okay? But it is polite conversation writing to join them together. Okay? Yeah. It's like when you put one, you spell out 1 and 2 instead of putting a number 1, number 2, right? Yeah. Doesn't really matter, but just better to do it that way. Okay, so again, this is going to be multiple groups. The prefixes for multiple groups again is di. Be careful. This is one of those places where it's a little bit weird. You will sometimes see bi. In organic chemistry, for the numbers of substituents, it's correct to put di. Okay? Bi would technically mean the same thing, but it is just not used for one reason or another. Right? So di would be 2. Tri is 3. Tetra means 4, right? And you'd actually use those same prefixes that we would normally associate with, remember your rules of naming from Gen Chem? Way back in the day. Like the mono, etc. Yeah, it's the same naming pattern there. We just don't need mono. Not necessary. And to be very honest, you will very rarely ever see anything over tetra. Okay? At that point, you get so many of them, you just have to start giving up on that naming. Okay? Kind of like how polymer works, right? Same thing. We have the dipolymer. So dimer. We have trimers, and after that, polymer. Give up. That's chemist for you. Can't count above 3. Okay. Anyways, does anybody have any questions on that? Okay, so again, these are the iso groups. Remember, the iso groups always has that 3 carbons making a V shape at the end. Okay? And it's not iso if one of these carbons is moved down the chain. All right? You kind of have to be careful about that. Now, you may notice that we don't do anything like, you haven't seen iso-sec, have you? Like if we had another substituent here, we haven't done anything like that, have we? Okay. We'll have complex substituent naming that will come up, and you abandon using this simple naming method, okay? At that point, you don't go iso-sec, blah, 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 okay? You name them like their little parent chains. All right? But we'll go into that in detail. Just know that if it starts getting more complex than these, you don't use iso-sec and all that. Right? That's for if it just has that specific group. That's not like a new IUPAC naming where you then like infinite loops. All right, so let's do a problem. Okay, so this is kind of the first time we're going to be doing a solved problem, so let me lay this down for you so you understand these better. When you see these, or if you see these in a recorded lecture, okay, then what you should do is, in lecture, what I'm going to do is I'll ask you the problem. As soon as you see it, you should start sort of working on it, okay? And you're going to need something that you can actually work on these, all right? If you have a tablet or something you can do it on, that's fine. I don't really care. Though I would recommend something that you are comfortable with using. Not, tablet. I'm using a tablet because I have it. So you'll start working on that. I'll give you like a minute or two to try to make some real progress, okay? If you're watching the video, pause the video and attempt to do the problem. You will get very little, if anything, out of this from just listening to me solve it, okay? Okay. The best thing you could do is actually attempt this problem from scratch for at least 5 minutes if it takes you that long. And then after 5 minutes, then you'd see how I did it. You would then go back in your notes, back in the lecture notes, and try it again from scratch later, okay? And see if you can then solve it then. If you can't, then you need to ask me, Dr. Clausen, how the hell do I do this? Right? You're going to feel brilliant when I explain it and like, I know all of this. And then you're going to get home and you're going to find out that some of these problems you're not going to be able to do, even though you thought you knew. Okay? So please do actually attempt these things. You're really going to be shortchanging yourself if you don't. Okay, so again, give the structures of 4-isopropyl octane and 5-T-butyl decane. So you can write out these structures. I would actually recommend doing them in line edge format, but you can do them in the condensed structure as well. That's fine. Line edge is faster. Don't forget at the end of these problems, always double check and actually count out your carbons. Okay? It's very, very easy to get add or subtract one when you're drawing these out. Okay? We making good progress? Bless you. Okay, let's go ahead and start working on this together. Hopefully you made some pretty good progress there. Okay, so when we look at this name right here, what are the important parts we need to look at and start deciding? We need the parent first, don't we? And so octane means what? 8 carbons. And so we make a chain of 8 carbons, don't we? Okay? And then we see 4-isopropyl. Okay, so we need to then draw a bond coming off of 4, don't we? Okay, and then what's the next part? We have a side chain there that has how many carbons? A pro is 3. Yeah, you got it. Okay? And so we have a side chain with 3 carbons, but is it a straight side chain or something else? It's branched, isn't it? Yeah. So that side chain actually gets attached in the middle of those 3 carbons. So it makes that iso V shape, right? Okay. And so that's the isopropyl group right there. There's only one of them because we didn't specify any more of that, did we? And it's on the 4th carbon. So we go 1, 2, 3, 4. It's easier to write this going left from right, but you don't have to. Okay? You could have flipped this the other way, that's fine. Which would have been 1, 2, 3, 4 instead, in case you're curious. Did I actually need to write this in a straight chain like that, going left to right? No. Yeah, I could have written it going down. I could have written this, zigzagging all over. It just would be harder to read and do, right? Okay, anybody have any questions on that one? Nope. Fantastic. Okay, so the next one is 5-T-butyl decane. What does decane mean? 10. You got it. And so we have a substituent. It's on what position? 5. Very good. So the 5th carbon will have a substituent coming off it, right? Whenever I do these, I personally like to go ahead and just add a bond at those positions because it's going to need a bond, right? Makes my life easier. Okay, and so what's the next part? What's a T-butyl look like? Anybody know what the full name for T-butyl is? Tert. Tert-butyl. So what does that look like? What does tert remind you of? Kind of like tetra, like tetrahedral, right? Okay. So tert-butyl is going to have a carbon in the middle with 3 substituents off of it. See that? 3 methyl groups off it. Everybody got that okay? All right. So don't forget, you need those. There is some memorization that's going to happen here, though most of you will probably comfortably memorize these things from just pure practice. Okay? But if you are not I memorize things very quickly just from practicing, flip cards do help. Okay? All right. Let's talk about organizing multiple groups. Again, these are actually the names for those multiple groups. Very rarely do we go above tetra, but if you need them, every now and then it happens. These are the next ones: penta, hexa, hepta, octa, nona, deca, right? Notice they follow along with the same thing as the number of carbons, don't they? With the only divergence being there's no 1, and the 2 ones, 3 ones are kind of different. Okay? So again, right here we have multiple substituents. And this is going to be organizing those multiple substituents. You always do those based off of the alphabetical order. And remember that that does not include the numbering prefix. Okay? So please be careful about that. These now are the complex substituents. So these ones are going to be, if you have multiple substituents off of a substituent. Okay? Another way of just saying that is it's complex, right? It doesn't have a very clear name. And so the complex alkylic groups are going to be named using your longest carbon chain. It's like having a subparent, right? Okay. And that's basically what you do. Is you just take the IUPAC naming and then you use it again. Okay? It has all the same rules as the original IUPAC naming. The only difference is your parent is now a propyl, butyl, etc., right? Instead of a alkane. It's an alkyl group. Again, the carbon number 1 is already set for you in this case. The carbon 1 is the one that's attached to your parent, isn't it? Okay? So the numbering is already set for you. There you go. Does everybody understand what we're looking at here? There'd be a parent right here, right? That's where the parent chain is. We're just looking at the substituent now. Okay, so when you write out these complex substituent names, what you do is you name them kind of like you're doing an IUPAC naming, but just for that substituent. And you put that in parentheses, and it will be placed where the other substituents are placed, in front of the parent name. Okay? Let's practice these complex substituents first, and then we'll get it all together. All right, so this one right here, the first thing we need to do is we need to do our sub-parent, right? Or I kind of like using like the names for plants, right? So the parent would be like a trunk. Now we have the branch, and then these would be like the leaves off the branch, right? Okay. Okay. So the first thing we need to do is name the main chain. Where's that? One, two, three, right? Okay. Could I go down here instead? Yeah, I can do that. That's fine. Yeah, don't worry about it. Why don't I go up here? That's also 3, isn't it? But it's not as branched, is it? Remember, I want to take the one that has more branches to it. Okay? So the one that has more substituents is the one I would choose. That only has one substituent. Okay, so I go 1, 2, 3. 3 carbons is, propyl. Very good, you did the propyl instead of propane. Okay, remember when we're the substituent, it's propyl, right? Okay, and then I'm going to have the substituents off of that substituent. All right, so this would be a what? Ethyl, exactly. And that one would be a methyl. Very good. And remember, my numbering is always set. Can I go 1, 2, 3? Start here? No, I can't, can I? Because I have a parent here. I have to count from that parent, don't I? Okay? It's where my origin is, where my start is. Okay, so I have my 1 position with an ethyl. Ethyl goes first because it's alphabetic, right? 2 position has a methyl. That goes next. And then I put a propyl. I put parentheses around it so I can designate that this is all one substituent. Okay? If I didn't put the parentheses, what would that say? That would say this ethyl is on the first position of my parent, right? Yeah. Without the parentheses, the entire meaning of that completely changes, doesn't it? And I've really screwed up. Okay? Okay. Right here, we have 4 carbons, butyl. This has 1, 2, 3 methyl groups. So that would then be trimethyl, right? And we put the numbers that they're attached. So 1, 1, and then a 3. Okay? Anybody have any questions? Well, let's practice it. Give me the systematic IUPAC name for the following compound. Remember, just take it step by step. First step's always what? Parent. Get your parent. Longest continuous chain. Most substituents. Once I have my parent, all I have to do is just make a little cloud of the substituents on there, right? Okay. Then I can assemble the substituents in front of that parent. By the way, the easiest way to work these problems is typically to go ahead and copy it down on your paper, and then you can number yourself if you want. At some point, you'll get so good at it, though, you'll just do it in your head. Yeah. Normal practice thing, right? Kind of like back in the day with Lewis structures. Okay. Let's go. Okay, so what was my parent? Heptane? Octane. Okay, so let's do both. Heptane? Okay. Octane. About even. Cool. Octane. Yep. So that is it right there. 1, 2, 3. A lot of you probably got stuck here, didn't you? Yeah, so don't forget, it does not have to be, left to right, straight on the paper, okay? It can be whatever zigzags. Be careful about that. So 1, 2, 3, 4, 5, 6, 7, and then 8 up here, right? Okay. By the way, is there any reason I don't go like there or there? That is totally fine. Yeah. It's one of the reasons I want to keep pointing that out for a little while. Is this is not arranged like it is on the paper. It's flip-flopping everywhere all the time. The bottom, top, left, entirely arbitrary. Yeah. Totally doesn't matter. Okay? Okay, so then I go through and identify my substituents, don't I? Okay. So I have methyl, 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 methyl. That's 4 of them. Right here, that's an isopropyl, isn't it? Hmm? Yes. The iso I. We don't use the numbering. Yeah, we don't use the numbering. So the number of them we don't use. Like if that had been di, tri, whatever, that wouldn't count. But the iso in isopropyl will count. That's okay. Honestly, getting the alphabetic order wrong, well, I'm going to take some points off and try to get you to do it right. If you publish this, this would not be something that they'd reject your paper for or something like that. This is not that big a video. And if you put it into a search engine, it would automatically correct you. So, yeah. Nobody's firing you over that. It doesn't really matter that much. Okay, so again, you number these. How do I figure out how to number my carbons? Yeah, I look for that first substituent to be the lowest number, right? And so 1, 2 versus 1, 2, 3, right? Okay, and then I go through, and don't forget, you can have them on the same 1, 2, 2, 3, and then this one would be 6, right? And so 2, 2, 3, 6, tetramethyl octane. And in front of that, I'm going to put on the 4th position an isopropyl. Okay. Mm-hmm.
So methyl is always going to be the last part?
No, we'll get to other substituents in a while, but you could have something behind methyl. Okay. But yes, methyl is often the last, but you could have nano, 9 carbon, right? N would come after N, so yeah. Or pentyl. But yeah, it oftentimes does, because a lot of your ones are going to be methyls and ethyls, and so yes, it does come along behind a lot. But if we had a straight chain propyl, that would come after methyl. Okay, let's talk about the degree of alkyl substitution. So again, here we have some different examples with some complex substituents. Okay. This is it drawn in with the parent right here. Do you want to go through and try to do that? We can. Okay, so you see you count out your chain, right? 9. That's your parent. And then you go your substituents off here. At first, you see an ethyl, and that's like, oh, that's nice. That's easy. I know that. And so you do 3 ethyl, right? Okay, so then in the 5th position, you see this group, and it's some sort of propyl something, but it's not really a isopropyl, is it? And it's not a sec-propyl. And so you go, oops, that's not something simple, is it? I have to do a complex name for that. Okay? And so then I put the 5, I put a parentheses, well, starter parentheses with 1, and then I start naming this like it's an IUPAC naming for a fresh compound. Okay? And so I go, what's my longest chain? Well, 1, 2, 3, or 1, 2, 3, right? This one's more branched. Okay, so I have a pro. This is a chain off my parent, so it's a propyl, right? Okay. Now, what are my substituents? I have 2 carbons here, ethyl. 1 carbon, methyl. My numbering would be, well, 1, 2, 3, because this comes off of here. And so it's 1 ethyl, E comes before M, and then it would be 2 methyl, and then a propyl. I finish my parentheses. I got that worked out. I can now finish my name by putting in the nonane, right? For 9 carbon parent. Okay. Everybody understands why I do that, like logic through the problem. I'm trying to expose the thought process behind you. At first, when you're developing your own thought processes and logical skills, you can follow my thought process and sort of lay yours over it. But eventually, you need to come up with your own, hopefully. Or become a clone of me, which, I don't know. That seems like a bad idea. Okay. Okay. I mean, not that my life's bad or anything, but, be your own person. Okay. I don't need any parrots. All right. So the boiling points of alkanes, again, as we get more branched, what's going to happen to our boiling point? It'll go down, actually. It'll boil easier, won't it? Okay? So as we increase molecular weight, the boiling point goes up. And that's what you see here. Number of carbons, increasing molecular weight, right? When we're straight chain, we're going to be the highest boiling point, aren't we? It's going to take more energy to boil. And that's because we have more London dispersion forces. What happens if we increase the number of branches, but don't increase the number of carbons? Well, if we're more branched, that's going to have a lower boiling point, isn't it? It'll boil easier. Okay? And that's what we're seeing here. Does anybody have any questions about these? Anybody know why this only starts here? Why don't I have like a lower number ISO here? Can you branch a 3 carbon chain? No, there's nowhere you could put the 3rd carbon to make it branched, right? Yeah. Those are just pure logic questions, I know, trying to make you be able to think. Okay, those are the melting points, same pattern. We'll start here on alkane sources, though I've already kind of hinted and talked about that a little bit. Anybody ever been to Ohio?